Welcome to another exciting episode of AP Chemistry here at Spain Park High School. If you're enjoying these videos anywhere in the world, please feel free to subscribe to my channel.
Awesome.
I was hoping that at some point I'll get more than 10 views.
Can you
All right.
monetize your videos?
I think after I get 11 views, then I can monetize it. No, I think I'm a long way from monetization.
Every 10 views is a penny.
Hey, it's quality, not quantity. It's the fact that, hey, I just need 2 or 3 people to benefit from this, and it makes it all worthwhile.
Yeah,
All right.
You won't get any money.
Yeah.
Hey, if I wanted money, I would not have become a teacher,
That's a good point.
okay?
True.
But you're a chemistry teacher.
Yeah. That's pretty
What
good.
if they didn't pay you? Would you still teach? No.
Not probably not.
That's a horrible question.
Depends on if I was like a bazillionaire or something. If one of y'all would go and just make $1 million bazillion and then bequeath some on me, then I'll have to make that decision. We'll see. All right, Le Chatelier's principle. So if we go and we have an equilibrium of SO2 gas plus 1/2 O2 gas goes to SO3 gas, delta H is less than 0. If I want to go through and I add some SO3 gas to this equilibrium, which way is the equilibrium going to shift? I add SO3. It's going to shift like yeah, don't make it hard. It goes away from whatever you add. If I add SO3, it's going this way. If I add SO2, it's going that way. Where's heat going to be in this one?
Right.
On the right side. Because it's less than 0, it's exothermic. So if I add heat, which way is it going to go? To the left. It always favors the endothermic direction. What if I increase the size of the container? It's going to favor the side with more moles of gas, which is left. Decrease the size of the container, right. Okay, so if I add sulfur dioxide or oxygen, it's going right. If I add SO3, it's going left. If I change the container, make it smaller, it's going to go right to fewer moles of gas. If I expand the container, it's going to come left for more moles of gas. Okay? If I add heat, it's going to go to the left. If I remove heat, put it in the fridge, it's going to go right. What's the only one that's going to affect the actual value of K? Temperature, heat. All right, that's really kind of what we did yesterday. The gist of that. Are we all good there? Now, what if I wrote, so let's just say that I'm just going to make a number, K here equals 10. If I wrote 2 SO2 plus O2 goes to 2 SO3 gases, what's K going to equal?
20. No, 0. No, 10. 10.
20.
Because you're
Just for the record, I have not heard the correct answer yet.
100.
100. Because I doubled it, so it's going to be 10 squared is going to equal 100.
Wait a second, that was a joke.
It is 100. Whatever, because the coefficients become the exponents. When you multiply the equation, then the coefficient becomes the exponent to K. It is written somewhere in there.
Oh, we got the AABB. Oh wait, no, sorry. CCDD over AABB. What?
Exactly. But it's A to the A times B to the B.
Yeah. I could write it.
All right. Now what if I said SO3 goes to SO2 plus 1/2 O2? What's K gonna equal?
Negative
1 over
10.
10.
I heard negative 10, I heard negative 100, I heard 1 over 10. Because products have become reactants, reactants have become products, so we're taking the reciprocal of the K, so it's 1 over 10,
Oh.
0.1.
Jeremy, you're killing it.
We good with that? And then again, if we have equations that add together, what do we do with K's?
Multiply.
Multiply. All right, so we need to know how K's vary. And again, the only thing that changes the value of K, as far as in a given reaction, the way it's written, is changing the temperature. None of the other effects. How does adding an inert gas do? What effect does adding an inert gas have on the equilibrium?
No effect.
No effect. What about adding a catalyst?
No effect.
No effect.
No effect.
Okay, we got that. All right, let's look at some math. Woohoo! You guys love it when I say that. There are, and I'm not going to necessarily follow the notes right now. I'm going to follow my own notes. It's all in there somewhere. There are 3 types. Well, actually, there's 2 types of equilibrium problems, but of the first type, there's 3 variations of it. So we're going to say 2 types of equilibrium problems. And during my lunch hour today, instead of eating lunch, that's why I had to eat the peanut butter and jelly sandwich just now, I was going through and looking at all of the old free response questions from 2021 through 2015. Very few of them are straight up equilibrium. They're probably going to be more in the multiple choice type question than a problem. So we're going to kind of go through these quickly so we can focus more on the problems that I found to be more prevalent over the past 6 or 7 years. Okay, so 2 types of equilibrium problems. In general, one, you're going to be given Ks, Kc, or Kp, and you have to find equilibrium concentrations. Or you're going to be given equilibrium concentrations having to find Kp or Kc, either one. So just given one, find the other. So back and forth. So let's look first at calculate the value of Kp or Kc. Given initial, I'll just say given equilibrium concentrations. Okay? Now, there's 3 different ways in which they're going to give you those equilibrium concentrations. The first one, don't hold your breath for. All equilibrium concentrations are given. So in other words, they just give you everything. Now here's the key word. It has to be equilibrium concentration. I guess that would be key phrase, 2 key words. Equilibrium concentration, not initial, not what you put in first, but once it reaches equilibrium, what are the concentrations of everything in there? So if we go and we turn and look in our textbook, chapter 15, this is the book I had marked in. Okay, on page 664. Page 664 in the textbook. We can look at question number 33. Okay, so this is an example of this type of problem. Well, pardon me, I think I'm on 32. 32 is the one I want. Stay. Ah, come on, you can do this. All right. Gaseous hydrogen iodide is placed in a closed container at 425 degrees where it partially decomposes to hydrogen. Now notice here, this is a key word too, partially. That's going to tell me that equilibrium is established, that it's not going to decompose completely. If it decomposed completely, then it'd be a stoichiometry problem, not an equilibrium problem. All right? So that's a key word. When it's something's partially, you don't need to see me, partially decomposed, that's simply going to mean equilibrium is going to be established. It only goes part way. So here's my reaction. At equilibrium, so it's found now, my HI is this, the H2 is that, the AI2 is this. Notice again it says, at equilibrium, and we're going to look at comparison to where initial volumes are put in versus at equilibrium volumes. So we have to be able to break the problem down and make sure we read everything, because the words tell us kind of what we need to do. So we have, this tells me we're at equilibrium, but this is telling me, okay, these are my equilibrium concentrations, which are the ones that have to go into my equilibrium expression. So what would be the equilibrium expression, Kc, for this? Just in general, the equilibrium expression, not the actual answer or anything, but what's the expression going to be? I2
times H2.
times H2. Now it doesn't matter the order. I probably would have done the other order because just the left to right, but again, it doesn't matter. Multiplication is commutative. Over
HI squared.
HI, and remember coefficients become power, so squared. So there's your equilibrium expression. So now how do we find Kc? Plug it in, plug it in. I2, 4.79 times 10 to the minus fourth. The H2 is 4.79 times 10 to the fourth, so are y'all good with me just saying squared? Divided by 3.53 times 10 to the minus third. Squared. Did you get it?
Yeah.
Okay, now Olivia's asking a question. I was just making sure she got the satisfactory answer. And apparently she did. Okay, what do we get?
0.0187.
0.0187. And what would the units be on that?
Cancel out.
There'd be no units, right? Because molarity squared divided by molarity squared, no units. Now, another question. Why are these two things equal to one another? Okay? So what was originally placed into the closed container? Just the HI, correct? So why is the H2 and I2 the same number? It's a very easy answer. Same number of moles. It's a 1 and a 1. Therefore, they're going to make the same amount. That's going to be kind of an important factor here as we move on. Okay, so that's the easiest type. I'm not even going to do another example problem like that. You're just given everything. You write your equilibrium expression, you just plug it in, you get your value of K. Don't expect one of those. Second, let me word it the way I worded it. An initial amount of a reactant is given, and equilibrium concentration of reactant or product is given. Oh man. Let's look at number 35. As a practice of this. Okay, so it says a mixture of 0.1 mole of NO, 0.5 moles of H2, and 0.1 mole of H2O is placed in a 1 liter vessel. The following equilibrium is established, and then at equilibrium, the NO is given as 0.062. So notice here, these are placed in the vessel. So are these in equilibrium concentrations? No. These are just what you put in initially. So that's why you have to watch carefully on this. This is where I really meant to have Vanilla Ice, Ice, Ice Baby playing. Okay, Ice, Ice Baby. Okay, that was close, right?
Yeah.
All right, because we're going to do what's called ice tables. Initial, change, equilibrium. An ice table. Now, a lot of teachers have you actually draw out the ice tables here and do all that. I like to be efficient, so I make my ice table right around the equation. So, and I go with my initial concentration, I. Well, it tells me a mixture of 0.1 mole, and that's in 1 liter, so the moles and molarity are going to be the same. So it's 0.10 molar of that, 0.050 molar of this. How much N2 was put in?
None.
0. No mention of it at all. So if it didn't mention it, they didn't put any in. And then lastly, 0.1 mole of H2O gas. So that's my initial concentrations. So now, as it approaches equilibrium, what's the only way initially when we put all of this in, what's the only way this reaction can go, and how do you know?
It can only go right.
Why can it only go right? Is that what you, I don't know what you said.
Alright,
It can only go right, why?
Because there's more
No,
about
not necessarily.
because you're adding stuff onto the left side. So it's
Well, but you have stuff on the right side
There's
too.
no nitrogen to make the equation go left.
Say that again?
There's no nitrogen to make the equation go left.
You can't go right to left because there's no nitrogen for the water to react with. So when you have a 0 of anything, it's got to go towards the 0, because 0 can't react. Does that make sense? So I know it's got to go left to right. That's important to be able to figure out which direction it's going to go to start initially. It's got to go left to right. So my change, how much is it going to change? That's the C. It's going to go to the right. Well, how much to the right? Well, I don't know how much it's going to go to the right. But I do know that at equilibrium, my NO is going to be 0.062 molar. So they tell me at equilibrium is that. Now comes in stoichiometry. Well, if it went from 0.1 to 0.062, what was the change? .038, correct?
Correct.
So it is minus 0.038 molar. And for every 2 of these, how many of those reacted? For every 2 react, so what's the change gonna be in my H2? Minus 0.038 molar, so at equilibrium, this one's gonna be 0.012 molar.
0.014, right?
Well, 38 to 50 is 12, isn't it?
Oh, okay.
Now, we had 0 to start with here. Now, if it's going to the right, this is gonna be being produced.
Plus
So this is gonna be plus how much?
0.038.
No,
1,9, because it's a 2 to 1. For every 2 that react, only 1 NO gets formed. Well, for every 1 N2 gets formed. So it's gonna be plus 0.019 molar with plus 0, so at equilibrium it's 0.019 molar. And what about this one?
Plus 0.038.
This is gonna be plus 0.038 molar, so at equilibrium, this is gonna be 138. Ice, ice, baby. Set up your ice table. So now we know everything, right? So now it's just like the previous problem, now we just plug it in, plug it in. Y'all know that that's a commercial, right, for plug in,
What?
air fresheners, plug it in, plug it in. You've never seen
know
that
Febreze.
commercial.
No.
I assumed it was just like a song that you like to sing.
Well, it's a commercial song.
I thought it was some of your repeating.
Well, plug it into the wall.
Yeah, you plug it in the wall out and it just freshens the whole room. It's just plug it
So
in.
the
It's a
jingle.
Glade plug-in, yeah.
The jingle is just plug it in, but twice.
Yeah, plug it in, plug it in. That made me remember it. Okay, so now, since this is all concentration, I want to do Kc is equal to my products, 0.019 times notice the 2 is going to play twice because I had to double it and then I squared. So over here, it's going to be 0.062 squared times 0.012 squared.
Why is it squared?
Because the coefficients are your exponents.
Oh, okay. 6.196 times 6.
Okay, so actually just 2 sig figs, so 6.2
Yes.
times 10 to the
7.
positive 2.
Yes, it is.
Does somebody agree with that number? I just always, y'all, everybody has trouble with calculators, and so I'm always double checking.
I actually got mine this time.
Wow.
On the bottom of my card.
Yeah. Did we not get that?
Maybe.
That's why, again, with the squares and dividing and whether you use parentheses or not.
Yeah, it's 6.5. Yeah, it's 6.5.
Matthew, what?
So why is it 0.038 again? Yeah.
Because it tells me my initial concentration. It tells me my equilibrium concentration is this. So the difference between that and that is that. 0.062 plus 0.038 equals 0.1.
Well, I got 6.5.
Yeah, 6.5.
Times,
10 to the second.
okay, so just 5.
Uh-huh.
Alright, so the question is this. Is this a product favored or a reactant favored reaction?
Does it ask us that?
I'm asking you.
Yeah. Mild guess.
What is K a ratio of?
Products to reactants.
Products to reactants. So if it's greater than 1, which one do you have more of? Products. So is this number greater than 1 or less than 1? Way greater than 1. Therefore, it's very product favored. If it's less than 1, that means denominator's bigger. That means reactants are bigger. Means it's reactant favored. So, when you're given an initial concentration and then an equilibrium concentration, you use your ice tables to figure out what the change was, and then know stoichiometrically the change has to follow whatever the coefficients are from your balanced equation. Okay? So, let's see you practice one.
I think that's pretty sure the
36 just makes it a little bit more challenging in that it gives it to you in grams rather than molarity.
Oh, shoot.
So what does that mean you have to do? You gotta convert to molarity first, and it's 2 liters, not 1 liter.
What problem?
I guess you.
Number 36, the one that's on the board.
That's also never mind. Actually, you technically do.
Go ahead and tell me I have some out of you left.
Oh, good. Mixture of. That's a lot of decimals.
Are you good?
That's just too many numbers.
What's the move after bromine?
Bromine, 79.9.
How does that make any sense now?
Oh, it's a 2-liter vessel.
There's not enough to make a big amount if you put it.
Oh, brother.
Yeah.
Yeah.
No, you weren't.
I guess.
You got it.
Don't say
I've
that.
already
She's not here. How is that supposed to work?
Through the camera.
You just do so goalkeeper. What'd you get? I asked you first. What? How did you didn't do it? Did you?
Oh, yeah.
I didn't even put it. 79.904.
Oh, yeah. 4.
What?
We divide by 2. It's 2 years. No. Oh. You're right.
Oh, no, finish the sentence.
Oh, did you?
No, please. Go back to where. Good job.
That's nice. You feel me, Josh? Oh, Josh. That's a real brother right there. What?
Oh my god. Okay, practice cycle.
That's like hilarity.
Ehrman.
Yes, it is.
Ehrman, are you breathe? Breathe here. Okay, go breathe.
Hold it in. Hold it in until it's okay. Hey, got bubble gum.
What?
Why would try that again?
Did you just say vitamin movement?
I said bubble gum. I said bubble.
Not you, I'm trying to figure out.
Josh, you said again.
Oh, what?
What? No, I didn't.
Did too.
I am a tiny.
You guys does good.
I'd rather just.
Yeah, but that's.
You know, I just found out I have to pay $1,800 to the federal government. Taxes.
You don't pay taxes, Germans.
What am I
Yeah. No, it's zero.
Do we add them to get HBR?
I guess we do.
Well, how do we get HBR?
It doesn't say, so it's gonna be 0.
Oh, Josh is smart. Boy.
I mean, I need confirmation, but.
Josh is smart, man.
Josh is smart.
Nah, he's.
Whoa.
What?
He
Whoa.
probably is. Gearman, are you high? That's Josh's job.
Whoa, guys. Hey, let's not.
Oh, hey, let's be nice.
Your rug.
I'm not that nice. To me, he's having to use like the poster of government.
Yeah.
Gosh, I may be slow, but I'm not that slow. Yeah. Yeah, well, he doesn't is much worse here.
Wait a second.
What he said, is it because I'm an immigrant, Josh? What he said? Are you saying immigrants?
Josh, that's so mean.
Okay.
You're so racist,
I
Josh.
don't know. You don't repeat it?
Okay, are we done?
No.
Then all, quit all this talking.
No, wait, I got.
I think
I definitely got something wrong.
I messed up.
This is fun.
Good, here's a whole bunch.
Oh, coach.
I heard we were having an overabundance of trees, I'm just trying to. Here's Mark.
Don't worry.
Yeah, where are you?
Don't worry, this is gonna go to the landfill and like.
I'm trying to find the chain. I got the chain. Basically,
Bro, we don't even have to connect.
Well,
What?
well, look on the right side.
I get used to it. You would have to. It's this. The chain.
Might as well go ahead and give you this one too.
This is the chain. Well, that's not good. I'm going to the negatives.
Okay, I don't.
Oh no, it's H2.
Oh, on board, yeah.
Wait, you used H2 for this? I had H for that.
So then I,
I'm
and
sorry.
then you have to calculate, physically calculate,
I didn't have a job. Why did I have to make it H2 BR2?
Okay, somewhere.
Oh, okay, you're right.
Because that's the way they exist in nature.
Yes.
divided by.
Oh, I can just divide everything by 2.
I've got it somewhere.
Yeah, that makes a lot more sense actually.
Contain 0. Oh, okay, wait.
Thank you, Dad.
And Mr. House finishes before me. I gotta beat him.
Excuse me, oh, bless you. That was a hiccup. Divided by.
Good job. Right?
1.01.
It's not that bad. I was reading just one more.
Yeah, 2 liter.
I just forget about the phone. Yeah, I know, that's what.
Seventy-one point nine zero.
No, I don't know, that's what, I guess she said something about college.
No, I see, yeah.
You know this one's
Closer, right? Like, almost the same distance.
What?
if you speed it's like
God, what are you doing?
I got this.
you have to work at prep school?
What?
Should BR2 be 160?
Yes, it should. I was getting there. I would have seen it as soon as I did this.
It's not my fault.
159.8.
I'm gonna make quits now, baby, I'm alright.
Yes, I think we've done it.
Actually, it's not mold, it's molarity.
KC?
Okay. At equilibrium is found at 1.556 grams.
So you did not get 57.4. Because you got 0 and then you gotta double it. Right? Is that what happens?
Where did this come from?
Yeah.
Wait.
Oh. They're not even here, they're at the house.
Okay.
I had a really big answer, that means it's not right.
So what did you get?
I get 58.
I got 57.
I'm probably more right.
Probably.
I use 7
I got
decimals.
57.
Yes.
Yeah.
I got 57.14.
Yes. I mean,
So I'm probably wrong.
It's okay, you use 7 decimals.
How many do you use?
Whoa.
Got it.
Oh no.
Is it? I thought it was always 3.
Yeah.
Why would it
I don't think it's always.
Oh, the majority of the time.
Well, yeah, but why did you say you use 7 decimals?
Because I did. But I thought mine is
I'm
like
not taking the
precise.
math yet, but I'm pretty sure 7 is not.
That's a good, I think we should follow
Because
that.
at this point, if it's one sig thing and you use like 1,000 versus what it actually is,
Why
1,000.
is it not, I guess that's, I'm not on that.
I think you have to get the
I think we should.
Why is this method
We're
hard?
gonna change the world one day.
Dude, did they show?
I gotta, Mr. Hobbs, I gotta talk to Graver.
Why?
Yeah. No, not about sick pay.
Initial change equilibrium. Why is there?
Ask him. I have to go ask him what he's doing for the rest of the
Oh, is he gonna participate?
Yeah.
Why?
Yeah.
I mean, I get.
Dash asked Graver what song he's gonna do, or.
Trying to motivate y'all.
Wait.
Vanilla ice, ice.
But.
Mr. Carbs and David Boyd specifically?
Yeah, they usually do. Don't they get sued for
It was a-
He's not doing the lip sync battle. He dropped out.
Was he ever in it?
Yeah, he said he's gonna do it.
I don't get it.
Cameron, you can do that, can't you?
Yeah.
That's like 80s. It looks like 80s.
I was going with Carbs.
It gives 80s vibes.
Maybe that's
Hey, get that song just playing in your head. Anytime you see an equilibrium problem, ice, ice, baby.
Ryan should be walking by, I'll be singing this.
Maybe we can get the whole AP class to get up and do the ice, ice, baby dance for talent, hey, if y'all be my background dancers, I'll do it.
Wait, are you serious?
But we'll see.
No, we're making the posters right now. So you have to be in.
Yeah.
May?
Huh?
Isn't it like in March or April?
We're making posters so everyone can type up what they're doing.
Oh, we should get monitored by the talent show.
Oh, it's still recording.
Oh,
This one.
yeah, you too, because you go like, okay, right, okay.
Yeah, they probably
YouTube
do.
section.
I really probably need to listen to the words of this. I don't have really any idea what they are.
Don't worry, I'll make kids.
It's like gibberish almost. Don't you know what they're saying?
I guarantee
Okay.
nobody in that video is gonna be able to hear.
Where's my phone?
Just amazing. All right. I was gonna try and do it with that on there. I can't. I just feel I can't try to control it.
I mean, you can have a certain tempo to the problem solving. Like. That'd be cool.
And once you get all this moving, it's very hard to get it stopped. It's just a physics thing. Yeah. All right, so I have calculated the initial concentrations, okay? There is my equilibrium concentration of H2 based upon the given. Are we all solid with my calculations there?
Solid.
So now we do our ice baby. We do our ice table. We have our initial concentration, 0.339 molar. We have 0.220 molar. And how much of this? Zero. That's what I got.
Hey, that's what
Thompson, you go touch
Did you use these numbers? Well, you might want to put it in the calculator. Okay, now what's my change in equilibrium? Well, in equilibrium, I have 0.140 molar of H2. So what must be the change? Point,
Yeah, it's like
Negative
0.2, negative 0.2.
well, it's not, it's 0.201, isn't it?
Why?
I mean, for
Well,
everybody that
okay.
used a 0.34 instead of 0.339.
What did you use something different here, 2.0178 or something?
My answer
No.
came out to be like, hold on.
Okay, well,
It was like something after 9 that would have caused it to round up.
oh, I didn't see that, but anyway, okay. So, minus 0.2 makes it easier. So what's this one gonna be? Minus 0.2. So that's gonna leave it as 0.020 molar. And then what's this one gonna be? Plus 0.4. So it's gonna be 0.400 molar. Now I'm doing this on a problem on a test. I don't rewrite this twice when it's 0. Okay? I just know that it's 0.4 and just go from there. Okay? I'm showing you this one. Yes, sir.
I got 0.082.
For which one?
The
Down here?
no, up there.
You're starting with this, the same number for every one of those, one of those. You're gonna subtract 0.2. 2.22 minus 0.2 is gonna be 0.02. Okay, come on, you're missing the simple math part. Alright, so now we have our equilibrium concentrations. Now, I'm hoping to get actual ring.
Wanna learn some AP chemistry?
Oh, God.
Not
This
bad.
is the two X. Okay, so put this
Yeah.
under me. Okay, now, the 3x is gonna be in this orientation, give me a finger. So
Lily and Anya, you are missed.
so big.
Wait. You missed Ice Baby.
No,
I'm
it
gonna
was
get
there.
one.
They
Oh,
did.
They heard it?
No, it has one. Let's see if I can get it up.
Oh, my bad, my bad.
Actually see it, put it on and feel it. But, the 3x is only 265, which I thought was relatively cheap
Wait, what was it?
for that design.
Why wouldn't you teach your chemistry bench?
Well, they don't mind the distraction. They're supposed to be at a break right now anyway.
Like, it's like this.
We didn't get a break yesterday.
Yeah.
The whole day was a break.
Oh,
Can
come
we
on.
get our break? Is it break time?
What is
I think.
The initial concentration, which I calculated right there, it says a mixture of this grams and that grams is heated. That's how much you put in. That's your initial concentration. the change, because it tells me at equilibrium, it tells me at equilibrium, I have this much. So which means that I have that much at equilibrium, the 0.14. So obviously, if it went from this to that, I have 0.021, but everybody else said that this was 0.340. So 0.2 must have been how much reacted. If we start with this and we end with this much must have reacted. Are you sure you got it? Okay? So we're trying to figure out how much actually reacted. So now we just go and plug it in. So KC is going to equal 0.4 squared divided by 0.14 times 0.02. And all that comes out to equal
57.1.
okay, and we end up having, well, how many sig figs throughout there? We have 3 and 3, 3, we should have 3, but this ends up only being 2, isn't it? So 2 sig figs, it's 57. So is this a product favored or a reactant favored reaction? Product favored, because it's greater than 1. All right, now do we really need a break?
Yes,
Yeah.
please. Your phone needs a break too.
Huh?
It's going on 50 minutes.
Okay, you can pause it, but
I mean, you
they're still gonna,
stop
there'll be
it.
a second video.
Oh, okay.